Okay, so yeah, let's just do this together real fast. So to find the inverse of a function algebraically, recall that f of x, the function output, is the y value. So the method we learned back in unit 3 to find the inverse is you switch x and y, and then you solve for the new y. Okay, so in this case, I would maybe subtract 3 from both sides, and then divide both sides by 2. Okay, so that would be one way to get the inverse. And remember, the inverse notation looks like this. Okay, so it's not f to the power of -1. It has nothing to do with exponents at all. This is just how you write the inverse of f of x. Okay, so we discovered this pattern by first making a table of values, actually. So if we go back to the original function, y equals 2x plus 3. All right, so if x is 0, 2 times 0 is 0, plus 3 is 3. If x is 1, 2 times 1 is 2, plus 3 is 5. If x is 2, 2 times 2 is 4, plus 3 is 7. All right, if x is -1, 2 times -1, -2, plus 3 is 1. 2 times -2, -4, plus 3 is -1. Okay, that's the original table of values. But again, we learned that the inverse undoes the action. So the original function took in a -2 and outputted a -1. Inverse takes that -1 and gives you back the -2 that you started with. Okay, and then lastly, we learned a property of functions and their inverses on a graph. Okay, so here I'm going to graph the original function. -2, -1, -1, 1, 0, 3, 1, 5. 2, 7 doesn't actually fit. Okay, and then I'll also graph the inverse. So -1, -2, 1, -1, 3, 0, 5, 1. Okay, could anyone remind us what we discovered about the graphs of the original function and its inverse? What do we see? Yes, Rebecca? Perfect. Rebecca said it's a reflection over the line y equals x. Okay, so remember, these patterns are true for all functions and their inverses, whether it's a linear function or a cubic function, or as we're going to see today, a trigonometric function. Okay, so trigonometric functions, the topic for the whole semester so far, sine, cosine, tangent. Okay, so we're not going to do the full table of values. We're just going to do the key values. Okay, so let's remember that for the unit circle, right, we'll even go back to degrees, right? So 0 degrees, 90 degrees, 180 degrees, 70 degrees, and 360 all the way around. Okay, so sine is the y coordinate. So at angle 0, you're at 0. At 90 degrees, you're at the top of the circle. So that's, for a unit circle, that's 1 unit up, +1. Right, 180, you're back at 0. 270, now you're in the negatives, so you're 1 unit down. And 360, you're back at 0. Okay, so again, we're just going to do those values in the interest of time. Okay, so the inverse function of sine is very creatively named inverse sine. Okay, so just like with the inverse above, to get the table, you just switch x and y, right? The old y becomes the new x, and the old x becomes the new y. Okay, so 0 degrees comma 0 becomes 0 comma 0 degrees. 90 degrees comma 1 becomes 1 comma 90 degrees. 180 degrees 0 becomes 0 180 degrees. 270 degrees negative 1, negative 1 270 degrees. And 360 degrees 0 becomes 0 360 degrees. All right, so this would be part of the table of values for this function called inverse sine. Okay, but just from this small set of data, we already see a problem, right? So what exactly is wrong with this? It's not that I made a mistake, as far as I can tell. It's the actual values that we don't like. Okay, so again, why would this be undesirable? What about this table of values is not what we typically look for? Okay, let's give Matissa a chance. And 0 itself, right? Okay, so Matisse noticed that the input of 0 can lead to, in this case, 3 different outputs. And remember, we want functions to have each input only leading to one output, right? If you don't have that, it'd be like you go to a vending machine, you push the Coke button twice, and you get 2 different drinks, right? Every time you push the same button, you should get the same output, but that's not what's happening here. One time you push the 0 button, you get 0 degrees out. Another time you get 180 degrees out. Another time you get 360 degrees out. So the inverse trig function is not a function. Okay, so remember the reason this happened was because the original function was not what we called back in unit 3. It's not 1-to-1, right? Yes, every x in the original function leads to a single y, but the same y can come from 2 different x's, or in this case, infinite x's. Okay, so if you want to think about this graphically, right, we know that sine, the parent sine function looks like this. Okay, so the y value of 0 happens infinite times, right? The graph is periodic, it repeats. So that means that when you do the inverse, it's gonna not be a function because you have repeated repeated y values that become repeated x values. Okay, so what do we do to fix the problem? It's gonna be the same strategy that we used back in unit 3. Okay, so as a reminder, in unit 3, we said, okay, the original function y equals x squared is fine, but the inverse would look like this. All right, the inverse would not be a function. It would fail the vertical line test. So the solution, which seems kind of weird, it seems like it shouldn't be allowed. The solution was to get rid of some of the x values so that the inverse doesn't have those either. So now the inverse is a function. Okay, so the term we use for getting rid of some of the x values is we restrict the domain. Okay, so that means we only allow certain inputs, certain x values to be used. Okay, so as a reminder, we had to do this because the original function, it is a function, it passes the vertical line test, but it fails the horizontal line test. So when it fails the horizontal line test, its inverse will not be a function. Okay, so that's what we're going to have to do for these trig functions. We're going to have to restrict the domain. Okay, so let's go ahead and turn to the second page. Okay, so you may recall that this first graph is y equals sine of theta. I guess it's x here, but whatever, theta. Right, we know that it starts at 0, goes up to the max, mid, min, back to the mid. This one starts at the maximum, right? Cosine starts at the maximum at angle 0. Okay, and then here you have tangent of theta. Okay, so we need to restrict the domain so that the remaining portion is 1-to-1, meaning it passes both the vertical and horizontal line tests. Right now, the sine function passes the vertical line test, but it spectacularly fails the horizontal line test, right? A single horizontal line would cross it infinite times. Okay, so how do we do this? Okay, so the choice has been made for us, I don't know how many years ago. Okay, so for sine of theta, we're going to restrict the domain to being between negative pi over 2 and positive pi over 2. Okay, so we're going to keep what's in between, and we're going to throw away everything else. Okay, because if you look at this highlighted section does pass the vertical line test and the horizontal line test. Okay, so again, ignore everything else. It passes the vertical line test still, but now it also passes the horizontal line test, right? Within those boundaries, a horizontal line can only touch it once. Okay, so down here, we're going to say for sine of theta, in order for the inverse to be a function, it needs to be between negative pi over 2 and positive pi over 2. And can we use those endpoints themselves? Negative pi over 2 is -1, positive pi over 2 is +1. So yes, right, +1 does not occur anywhere else, so it's fine. Okay, so the domain is bracket negative pi over 2, comma, positive pi over 2. Okay, remember, domain is the input, the x value. And what is the range? Well, we can see that the range can still go as low as -1, and it hits every y value up to and including +1. Okay, so now this function, which remember, this is not sine to the negative first power, it's inverse sine, or it's also called arc sine. That's how you would say this out loud, either of these. Okay, so we know that for an inverse, you just switch x and y. So the old x, the old domain, becomes the new y, the new range. Okay, so you just switch the domain and the range. Sine's domain becomes inverse sine's range. And sine's range becomes inverse sine's domain. Okay, so now we're going to do a similar thing for cosine. Okay, so again, we need to somehow restrict the domain so that the remaining section is 1 to 1. So why don't we check, can we just do the same thing? Can we again do negative pi over 2 to positive pi over 2? And the answer is no, because now a horizontal line can cross the graph twice. Okay, so we have to do something different. Okay, so the choice that we use is from 0 to pi. Okay, so this section is 1 to 1. It still passes the vertical line test, but now it also passes the horizontal line test. And again, you can use the endpoints. So we're going to do bracket 0 to bracket pi as the domain. And the range, you don't say 1 to negative 1. You always go smaller number first. So negative 1 up to positive 1. Okay, so let's check if you guys are following along. You should be able to fill in this part in 3 seconds. Okay, so go ahead and see if you can tell me the domain and range of inverse cosine. Okay, so you just switch the domain and range of regular cosine. Okay, so those would be the domain and range for inverse cosine or arc cosine. Okay, and then lastly, we have tangent, which looks like this. Again, we need the section to be 1 to 1. Okay, so this one's already kind of divided up for us, right? So can we just use this section between the vertical asymptotes? It passes the vertical line test, and it also passes the horizontal line test. Okay, so here we can go between negative pi over 2 and positive pi over 2. But unlike sine, where you can use negative pi over 2 itself, it has an actual point. Here, negative pi over 2 is a vertical asymptote. So you can't use that x value because it's a vertical asymptote. Okay, so that means instead of using brackets for tangent, we use parentheses. Let's use a different color. Okay, so just like sine, it's between negative pi over 2 and positive pi over 2. But sine can use those actual points. Tangent cannot because they're vertical asymptotes. Okay, now what about the range? Well, this goes downward forever, this goes upward forever. So the range is negative infinity to infinity. Okay, and again, you should be able to do the inverse tangent, domain, and range pretty much instantly. And the domain of tangent becomes the range of inverse tangent. Oh, sorry. And then the range of tangent becomes the domain of inverse tangent. Okay, so we'll need to refer back to these throughout this 7.1 lesson. Okay, so when you're doing inverse sine, your answer can only be between negative pi over 2 and pi over 2. You're not allowed to give an answer of pi or 2 pi or negative 2 pi. It has to be between those two angles. Okay, so let's jump down here. Okay, so here we are asked inverse sine of radical 3/2. All right, so let's write in words what this is asking. Okay, so remember, this is sort of undoing the regular thing. So inverse sine of radical 3/2 is asking what angle has a sine ratio of radical 3/2. Okay, that's what this notation is asking us to figure out. Okay, so how do you do this? Well, one way would be to go back to the unit circle. Okay, so we know that 0 degrees is 1 comma 0, so it's not that. Next up, 30 degrees, it's radical 3/2 comma 1/2, right? But sine is the y value, so it's not 30 degrees. 45 degrees, radical 2/2, radical 2/2, it's not that. 60 degrees would be 1/2 comma radical 3/2. Okay, and that is the correct y value, right? So a 60-degree angle has a sine ratio of radical 3/2. So therefore, inverse sine of radical 3/2 is 60 degrees. Okay, now you probably remember that. Well, can't you keep going on? Can't you reflect this over and say 120 degrees? Yeah, the x coordinate is negative, but the y coordinate is still positive, right? The y coordinate is still going upward. So shouldn't 120 degrees also be an answer? Well, we have to go by the domain restrictions. Okay, so this is in radians. If you want to convert this to degrees, it'd be negative 90 degrees to positive 90 degrees. So you're not allowed to output 120 degrees because it's not between negative 90 and positive 90. Right? The whole point of domain restrictions is so that we only have one correct answer. Okay, so again, inverse sine, the answer needs to come from negative 90 degrees to positive 90 degrees. Right, so the answer could only have come from quadrants 1 and 4. It cannot come from quadrant 2 and 3. Okay, and so I did say in both degrees and radians. So let me convert 60 degrees to radians real fast. Okay, so 60 degrees or pi/3 radians. Okay, so let me do one more with you. Tangent's a little trickier because tangent involves both x and y. Okay, but inverse tangent of negative radical 3 is asking what angle has a tangent of negative radical 3. Okay, if you want to write this one in symbol, this is basically asking regular tangent of what angle equals negative radical 3. Right, so you got to figure out what angle leads to this answer. Okay, so let's use the domain restrictions. Inverse tangent has to be between negative radical 2 and positive radical 2. Okay, so again, in degrees, that would be negative 90 degrees to positive 90 degrees. Okay, so we don't need the full unit circle then, right? Because negative 90s here, positive 90s here. Okay, so the answer has to be between them. Okay, and then we also see that the output is negative. So we don't really need to bother trying the angles up here because tangent would be positive in all of these, right? Because the opposite is positive and the adjacent is also positive. So tangent would be positive. Okay, we know the answer is going to come from quadrant 4. Okay, so now here, again, you may need to write out the unit circle, right? So this first point, normally we would call it 330 degrees, but because it has to be between 90 and negative 90, we would instead call this negative 30 degrees. Oh, sorry. Okay, if you don't remember these, you can always draw the actual triangle, right? You say, okay, this is a 30-degree angle, hypotenuse is always 1. Opposite the 30-degree angle is half of the hypotenuse, so it's 1/2. But since it's going downward, the y-coordinate's negative 1/2. And then times radical 3 is radical 3/2 for the x-coordinate. Okay, that's how you could always do it if you forget the unit circle. Okay, now, is this the correct tangent value? Tangent is y over x, or sine over cosine. Okay, so negative 1/2 divided by radical 3/2. You could write that sideways. And then multiply by the reciprocal, canceling out the 2's. Okay, and then rationalizing it. Okay, so it's not correct. Tangent of negative 30 degrees is negative radical 3/3. We just want plain negative radical 3. Okay, so it's not negative 30 degrees. So we can try the next angle of negative 45 degrees. But you may recall that for a 45, 45, 90 triangle, these two sides are congruent. So it'd be 1/2 and negative 1/2. Oh, no, sorry. Radical 2 and negative radical 2/2. Okay, so if you do tangent of this one, it would be negative radical 2/2 over positive radical 2/2, and that'd be negative 1. So it's not that either. Okay, so it's going to be the last one, but let's just make sure. Negative 60 degrees, that has coordinates of 1/2 comma negative radical 3/2. Okay, so tangent of negative 60 degrees, y over x. Okay, so we see that tangent of negative 60 degrees is indeed negative radical 3. So that is the answer we wanted. Okay, negative 60 degrees in radian form. Negative pi/3. Okay, so it would not be correct to say 300 degrees. Even though negative 60 and positive 300 are coterminal, they do hit the same point on the circle. 300 degrees is not within the allowable range for inverse tangent. Okay, so you can't use coterminal angles. You have to use the angle within the given range. Okay, so questions on either of these examples? Yes? No? Oh, okay. Go ahead and take a couple of minutes then and try the rest of this row, please. Okay, so here I'm asking what angle has a cosine ratio of radical 2 over 2. Okay, so cosine is the x coordinate. So you may recall that radical 2 over 2, radical 2 over 2 is from a 45-degree angle. Okay, and you always want to make sure, is my answer within the allowable range? So for cosine, it's not negative 90 to positive 90, it's 0 to 180. So 45 degrees is fine. Inverse sine of -1, where is sine equal to -1? That would be down here, right? Now you cannot call this 270 degrees. Even though it is 270 degrees, 270 is not between -90 and positive 90. So instead of positive 270, you have to call this -90 degrees. Okay, and then lastly, inverse cosine of -2. Okay, so here I'm asking, where is the x coordinate equal to -2? Well, nowhere, right? You can't, the circle never gets to -2. The furthest it can go is -1. Okay, so this is impossible. Right, and if you look back at the inverse cosine, the domain is -1 to 1. You can't use -2. Okay, so we're going to continue this handout next class, so make sure you bring it back.